Chapter 3, Exercise 33. Show that R is a symmetric and transitive relation if and only if R is equal to R inverse composed R. For your reference, I've written down again what symmetric and transitive mean, though I did cover them in the last video, so I won't go over them again. Alright, the way I solved this was a bit unorthodox, and you'll see why in just a sec. But here is my answer. Let's prove in the forward direction first, and for that we're going to assume that R is a symmetric and transitive relation. And now the reason I say that it was unorthodox the way that I did it is because I'm going to show that this is a subset of this, and then I'm going to use that fact to show that this is a subset of this. Okay. So first, we're actually going to show this direction. So we're going to show that R inverse composed R is a subset of R. And for that, let's suppose that x comma z is in R inverse composed R, and then this means that there must exist some y such that x comma y is in R and y comma z is in R inverse. Right. Now, by exercise 3i, exercise 3-31. Is this right? This looks wrong. Did I cite this? No, 32. Alright, by the previous exercise, literally. Okay. We have two things. We have A, that R is symmetric if and only if R inverse is a subset of R, and B is that R is transitive if and only if R composed R is a subset of R. Right, so using fact A, by fact, let's call it 3-32A, YZ being in R inverse implies that YZ is an R. Right. So there exists some y such that x comma y is an R and y comma z is an R. Right? And given that R is transitive, x comma z must be in the composition of R with R. Okay. So, R composed No. This is wrong. Okay, sorry. I shouldn't read my notes. Okay. They're sometimes wrong. Okay. So, again, there exists some y such that x comma y is an R and y comma z is an R. And given that R is transitive, x comma z must be an R. Again, this is just xry and yrz. And this implies that xrz is true. There. That is the gist of things. Okay, so thus R inverse composed with R is a subset of R. Okay, And now what I'm going to do is take this as a fact, because that makes proving the next thing easier. And now we're actually going to show that R is a subset of R inverse composed with R. That may seem like circular reasoning, but it isn't. Okay, let's suppose that x comma z is an R. Then what? Then z comma x. Those look literally the same. What the fuck? Okay, then z comma x is an R inverse. So there exists some z such that x comma z is an R and z, why are they so difficult to draw today? Okay, z comma x is an R inverse, and thus x comma x must be an R inverse composed with R. Okay. Thus, capital B, by the previous part, and I'm going to cite this as just the symbol we used. R inverse composed with R is a subset of R, and thus x comma x is in R. Right, so now recall that z comma x is in R inverse. Sorry. No. Recall that x comma z is in R. By symmetry of R, z comma x must also be in R, and thus x comma z must be in R inverse. Okay, so there exists some x such that x comma x is in R and x comma z is in R inverse, and thus x comma z must be in R inverse composed R, meaning, of course, that R is a subset of R inverse composed with R. Okay, cool. So that's one part. And right, needless to say, R is actually equal to R inverse composed R. Okay, cool. And now we're going to show the other direction of this proof. To do that, we're going to assume what we just proved, which is that R is equal to R inverse composed with R. And let's now I have to show that R is a symmetric and transitive relation. So let's suppose I'm going to show that it's transitive first for whatever reason. Suppose that x, ry, and y, rz is true. Then by this factoid right here, x comma y is in R inverse composed with R, and y comma z is in R inverse composed with R. Thus, there exists some y such that I'm not going to use both of these facts. I'm only going to use this one. Okay, so there exists some y such that x comma y is an R inverse composed with R, and y comma z is an R. Thus, x comma z must be in R composed with R inverse composed with R. And my screen is lagging. I don't know why. I don't get it. I'm just very annoyed at this point. Okay. And now we proved in exercise 3-21 that composition is associative. Right? Meaning that x comma z must be in R composed with R inverse composed with R. So what now? All right. So x comma z is in R composed R inverse composed R. Did I show this before? Or actually, no, I haven't cited this before. That was in the previous botched recording of this video. Okay. By theorem 3i, let's call it S composed T inverse is equal to T inverse composed with S inverse. So R composed R inverse is actually equal to R inverse composed with R inverse, and which is equal, and I'm not going to justify it, that to R composed with R inverse. It should be easy to prove for you that these cancel out and just give you this. Right, so what does this mean? Thus, R composed with R inverse is actually equal to R composed with R inverse, which is equal to, or rather, so R is equal to R composed R inverse, R composed R inverse, which is actually equal to its own inverse, which implies that R is equal to R inverse. There. Okay, that's what I was trying to show. Okay, there. I got unstuck. Good. So, x comma z is in R inverse composed with R. And then finally, x comma z must be in R, because we assume that these are the same set. These are actually equal. Okay. Thus, R is transitive. Alright, phenomenal. Alright, now let's suppose that R is, sorry, x comma y is an R, and then x comma y is an R inverse composed R, and then oh right, which we showed that R is actually equal to R inverse. Actually, we don't even need this. And we can actually say that we not only show that, we just showed it. So, and actually, let me just justify this a little bit. This is provided that R is equal to R inverse composed R. That is our assumption, right? Yeah. So x comma y is in R inverse. Thus, that is a horrible thus. Thus, y, okay, there. Thus, y comma x must be in R. So, x r y implies that y r x. We conclude that R is symmetric I'm just guessing, hoping, because this pen is so laggy for some reason. But yeah, I think it came out legible. Cool. Phenomenal. Right, so, yeah, just to recap, we showed that R is a symmetric and transitive relation if and only if R is equal to R inverse composed R. This was, I don't know, it's just bothersome. I wish there was a faster way. I tried using theorems where I could. I mean, if you found a faster way to show this, please let me know. But honestly, I think you just have to do it like this if you want to be rigorous. It's okay. It's not that bad. There's worse proofs, but like it is kind of tedious. Why lie to you? This is pretty tedious. Hope you got through it in one piece. And yeah, I hope this video was helpful, and I will see you in the next one. Bye-bye.